Hello everyone. In today's video tutorial, we are discussing one numerical based on stresses developed inside the power screws, how to deal with the stresses, how to use values of stresses while designing the power screws. Today's session or today's discussion belongs to CO number 4, wherein after you studying this unit, students will be able to design power screw applications like screw jack and C-clamp. Now, up till now, we have studied the theory of the power screws. As far as this theory of the power screw is concerned, briefly, I have enlisted the different formulas which are relevant to the theory of the power screw. Inside the theory of the power screw, we have studied how to find out the total torque required to operate the application, which is given by Tt plus Tc. Total torque required to operate the application is given by summation of torque required to raise the load or torque required to overcome the thread friction Tt plus the torque required to overcome the collar friction Tc. This total torque as given by the operator for operating the application, power screw application, T will be given by P multiplied by Lb, wherein P is the operator force and Lb is the length of the bar or length of the handle used by the operator for giving the torque. Sometimes the power screws are provided with hand wheels to operate them, to rotate them. In such cases, if hand wheel is smaller one, then we have to use radius of the hand wheel as the value of Lb, and if the hand wheel is larger one of the if the diameter of the hand wheel is of the order of 500 or so, greater than 500 millimeter, then it is assumed that the operator is rotating the hand wheel using both of his hands. Therefore, value of Lb is assumed as diameter of the hand wheel. Then this Tt, torque required to raise the load, will be given by WDM upon 2 tan of phi plus lambda. If you want to lower the load, in that case the torque applied to lower down the load will be given by WDM upon 2 tan of phi minus the lambda. Tt is the torque required to raise or lower down the load, which is also called as torque required to overcome the thread friction. In the formula of Tt, phi is the friction angle given by tan inverse of mu, and lambda is the lead angle, which is given by tan inverse of L upon pi dm, wherein L is the lead, which is equal to number of starts multiplied by pitch. Dm is the mean diameter. Mean diameter is equal to nominal diameter d minus half the pitch. Tc is the torque required to overcome the collar friction, which will be given by mu c w r of f or r of m. Mu c is the coefficient of friction at the collar. Sometimes in the given data, value of mu c is not separately mentioned. In such cases, value of mu itself is assumed as mu c to calculate value of Tc. Mu c is the coefficient of friction at the collar, W is the load, and Rf or Rn is the friction radius or mean radius, which is required to be taken into account according to the theory which is required to be employed. If you want to employ maximum pressure theory, then you have to use Rf, the friction radius, given by 2/3 of Rho cube minus Ri cube divided by Rho square minus Ri square, wherein Rho and Ri are representing equivalent outer and inner radius of the collar, friction collar. If you want to employ uniform wear theory, then you have to use Rm, the mean radius, which is given by Rho plus Ri divided by 2. Besides this, while studying the theory, we have also seen that efficiency of the screw and nut arrangement is given by tan of lambda divided by tan of phi plus lambda, and overall efficiency of the application is given by WL upon 2 by T. Based on this overall efficiency, one can decide whether the screw arrangement is a self-locking one or overhauling one. If the overall efficiency is lesser than 50%, then the arrangement is self-locking, otherwise it is overhauling. Overhauling means screw will get lower down of its own without application of any torque to lower down. Now we have already discussed that as far as stresses develop inside the power screws are considered, we have to deal them at two different levels. At the level of body of the screw, which is also called as shank of the screw, and at the level of threads of the screw. So as far as the stresses develop inside the threads of the screw, there will be direct shear stresses develop at the threads of the screw, direct shear stresses develop at the threads of the nut, and there will be bearing pressure develop at the interface of nut and the screw. These three values will be given by the formula as specified. The stresses developed inside the threads of the screw are irrespective of the application, whereas in case of stresses for the body of the screw or shank of the screw will be calculated considering what is the application. Based on the application, the formulas required to be employed do change in case of stresses calculated for the body of the screw. Irrespective of application, whatever is the application, the stresses developed inside the threads of the screw will be calculated by these three formulae always. Now, if application is not known and or application is not mentioned inside the given data in the problem statement, then we have to use these three formulae for calculating maximum stress developed inside the body of the screw. Body of the screw is many times referred as shank of the screw. Body of the screw will be subjected to compressive stress sigma c given by W upon pi by 4 dc square, torsional shear tau given by 16 T upon pi dc cube, and the nature of the stresses developed inside the body are of direct as well as shear. So it is a case of complex loading because two different kind of stresses are getting developed inside the body of the screw. So it is a case of complex loading. Whenever there is a case of complex loading, we have to employ a suitable theory of failure for calculating maximum stress developed inside the body of the machine part. Screws are generally made up of ductile material, steel ductile material, which is ductile material. And for ductile material, maximum shear stress theory is the most suitable theory. Therefore, for calculating maximum stresses developed inside the body of the screw, employing maximum shear stress theory, the stresses developed are calculated as under root sigma c upon 2 square plus tau square. Now let us solve one numerical wherein the idea will be getting cleared up. The problem statement is as shown here. For a power screw application using following data, we have to find out the torque required to rotate the screw. We have to calculate stresses developed inside the screw. We have to calculate height of the nut, and we have to also calculate yield strength of the screw material, achieving factor of safety as equal to 3. The specified or given data is isometric threads are being specified, which are designated as TR30Y18 P6LH. Load is 12 kilonewton. For the collar, outer and inner diameters being specified as 100 and 60 respectively. Coefficient of friction is 0.18. Uniform pressure theory is expected to be used while designing, and also they have specified permissible bearing pressure 3.87 megapascal. Now here they have specified trapezoidal threads, that means we need to use mu dash while calculating phi, the friction angle. Friction angle will be calculated based on mu dash. Mu dash is given by mu upon cos of theta, wherein theta is the semi-thread angle. Value of theta is equal to 15 for isometric threads. Value of theta is equal to 14.5 for acme threads. In this particular case, They are specified isometric trapezoidal threads. Therefore, using value of theta as 15, mu upon cos of theta, mu upon cos of 15 will give you value of mu dash. In this particular case, it is 0.1863. Its tan inverse will give you value of phi, the friction angle. In this particular case, that is, this friction angle is equal to 10.55 degrees. Now they have specified nominal diameter as 30, lead as 18, pitch as 6. Pitch is 6, lead is 18, that means number of starts is equal to 3. They have specified left hand threads for the screw. Now here dm is equal to d mean diameter is equal to nominal diameter minus half the pitch. So knowing the value of nominal diameter and pitch, we can calculate dm as equal to 27. Core diameter DC is given by d minus the pitch. D is 30, pitch 6. Therefore, DC is equal to 24. Lambda is given by tan inverse of L upon pi dm. L is the lead, dm is the mean diameter. All the values of L and dm are known to us. Therefore, we can calculate lambda, which is equal to 11.98 degrees. Now, they have specified load as 12 kilonewton, so 12,000 newton. Outer and inner radius, because they have specified outer and inner diameter, we need outer and inner radii, and values for those are, for RO its value is 50, for RI value is 30. They are asking us to use uniform pressure theory, therefore we need to use RF in the formula of TC. In the formula of TC we need to use mu c W RF, because they are asking us, or they are expecting to use uniform pressure theory. So we need to use friction radius, which is given by 2/3 of RO cube minus RI cube divided by RO square minus RI square. Value of RO and RI are known to us. Therefore, value of RF can be calculated, which is equal to 40.83 millimeters. They have specified only one value for coefficient of friction, and they have not specified coefficient of friction for the collar separately. Therefore, assuming same value of mu for collar also. So in this case, coefficient of friction at the collar is equal to 0.18. Now we are having with us value of mu c, value of W, and value of RF. So we are in position to calculate TC, the torque required to overcome the collar friction, which is equal to 88,200 Newton millimeter. Just I have carry forwarded the given data here. Now let us calculate TT, the torque required to overcome the head friction, or torque required to raise the load. WDM upon 2 tan of phi plus lambda. W is known to us 12,000, dm is 27, phi is 11.98, lambda is 10.55. I just by mistake I have swapped the sequence. Actually phi is 10.55 and lambda is 11.98. Okay. Then value of TT will be 67,202. Now we are having with us value of TT and TC both. Therefore, we are in position to calculate T, which happens to be equal to 1,55,402 Newton millimeter. They are asking us to calculate torque required to rotate the screw, which we have now calculated. Now, in this case, they are not specified any application as such. Therefore, we have to consider overall stresses developed inside the body of the screw. In overall stresses developed will be in the form of compressive stress given by W upon pi by 4 dc square, and torsional shear given by 16 T upon pi dc cube. Their equivalent maximum shear stress will be calculated based on the formula root of sigma c upon 2 square plus tau square. Now stresses develop inside the threads of the screw, threads of the nut, and bearing pressure at the interface will be calculated based on these formulae. Now just I have carry forwarded the things on the left hand side. On the right hand side, actually calculation for stresses inside the body of the screw or shank of the screw being done. Sigma c The compressive stress inside the body of the screw is given by W upon pi by 4 dc square. W is known to us, dc is also known to us. So sigma c is equal to 26.52 megapascal or Newton per millimeter square. Torsional shear stress will be given by 16 T upon pi dc cube. 16 multiplied by T, the total torque which we have calculated in the previous slide. DC is also known to us. So we are in position to calculate tau, which happens to be equal to 57.25. Now using the value of sigma c and tau in the formula, we can calculate maximum shear stress developed inside the body of the screw, which in this particular case happens to be equal to 58.76 megapascal. Megapascal means Newton per millimeter square. Now, maximum stress developed inside the body of the screw should be less than or in limiting case equal to permissible stress. Tau max should be less than tau permissible. In limiting case, that can be equal to. So here, while designing, always we are equating induced maximum stress with the permissible stress. So the same consideration will be assumed here. Tau max will be equated with tau permissible. We are knowing value of tau max, which is equal to 58.76. Tau permissible is given by SSY upon factor of safety. So 58.76 tau max is equal to tau permissible SSY upon factor of safety. Factor of safety is equal to 3. So here SSY will be given by 58.76 multiplied by 3. SSY is equal to 58.76 multiplied by 3. So it is equal to 176.28. But SSY is equal to 0.5 times SYT. So SYT is equal to SSY upon 0.5. SYT is equal to SSY 176.28 divided by 0.5. So therefore SYT yield stress, yield point tensile stress or yield strength will be equal to 352.56 Newton per millimeter square. So here for this particular application we need to use such a material whose yield strength will be greater than or whose yield strength will be at least equal to 352.56, greater than 352.56, but it is better if you are using yield strength greater than 352.56 Newton per millimeter square. Now they are asking us to find out the stresses developed inside the body as well as threads of the screw. So for calculating stresses developed inside the threads of the screw, threads of the nut and bearing pressure, we need to use these formulae. Here I have just carry forwarded the things. Permissible bearing pressure being specified as 3.87, but permissible bearing pressure is given by W upon pi by 4 d square minus dc square multiplied by z. So equating induced bearing pressure with permissible bearing pressure. Here, while equating, this is permissible bearing pressure and this is induced bearing pressure. In the formula of induced bearing pressure, only Z is the unknown because here W is known to us, D is known to us, DC is also known to us. Only Z is the unknown. So value of Z is calculated, which happens to be equal to 12.18 tons, which is rounded to 13 tons. Now Z, the number of threads in contact multiplied by pitch, that gives you value of height of the nut or axial length of the nut. In this particular case, that is equal to 78 millimeters. Now, once we know value of Z, in this particular case, it is equal to 13. T is the thickness of the thread, which is equal to half the pitch. Pitch is 6, so T will be equal to 3. So here, using these formulae, we can calculate direct shear stress developed inside the threads of the screw, direct shear stress developed inside the threads of the nut. Here, all the terms required to calculate tau s and tau n are known to us. W is the maximum load 12,000 Newton. DC is the core diameter 24. D is the nominal diameter 30. T is the thickness of the thread, which is equal to half the pitch, so it is 3, and Z the number of threads in contact, which are equal to 13. Okay, by mistake I have mentioned 10, it should be 13. So using the known values tau s and tau n can be calculated, which is equal to 4.08 Newton per millimeter square and 3.26 Newton per millimeter square respectively. So here by that we have answered all the questions. We have calculated the total torque, we have calculated stresses developed inside the body of the screw, stresses developed inside the threads of the screw, and also we have calculated the yield strength of the material required to be employed for this application. All the required things, all the required questions we have answered now. So that's all. In this PPT we have learned what are the stresses inside the body of the screw or shank of the screw, what are the stresses developed inside the threads of the screw and nut, and what is bearing pressure, how to calculate height of the nut, different sections of the screw are subjected to different type of stresses, we have studied that, and also we have studied how to find that different stresses develop inside the different sections of the screw separately. So that's all for this PPT. Thank you.